Today we are diving into the critical process of forensic data acquisition. When dealing with digital evidence in a legal or investigative context, we cannot simply copy and paste files. That would alter metadata and potentially destroy crucial hidden information. Instead, we must create a forensic copy, also known as a bit-by-bit image. This is an exact duplicate of every single bit on the source drive, from the very first sector to the last, including all unallocated space, where deleted files often reside. Our primary goal here is data preservation. The original evidence must remain completely untouched and unaltered to ensure its admissibility in court. Before we even touch a device, we must always ensure we have the proper legal authority, such as a search warrant or owner consent. In this lecture, we will explore the specific techniques for acquiring data from traditional hard drives, modern solid-state drives, portable thumb drives, and complex mobile devices. Before connecting a suspect device to your forensic workstation, you must adhere to the golden rule of digital forensics. Always use a write blocker. Modern operating systems are designed to be helpful. The moment you plug in a drive, they start writing data to it, creating hidden files, updating access timestamps, and indexing content. This instantaneous alteration compromises the integrity of your evidence. A write blocker is a tool designed to prevent this. It sits between the source device and your computer, allowing read commands to pass through so you can image the data, but physically blocking any write commands aimed at the source. While software-based write blockers exist, hardware write blockers are the industry standard and highly preferred. They are separate physical devices that provide a higher level of certainty and are generally more trusted in legal proceedings because they remove the variable of OS behavior. Let's start with traditional spinning hard drives and USB thumb drives. The acquisition process for these is very similar. First, you identify the drive's interface. Is it an older IDE, a standard SATA, or USB? You then select the appropriate adapter and connect the drive to your trusted hardware write blocker, which is then connected to your forensic workstation. Using validated forensic imaging software, you will initiate a physical or bitstream image. This process reads every sector on the drive sequentially. Because it's a physical copy, it captures everything: current active files, the space occupied by deleted files that haven't been overwritten yet, and the drive's unused space. A common challenge with older hard drives is physical degradation leading to bad sectors. Your imaging software should be configured to handle read errors gracefully, typically by logging the error, filling the unreadable sector with zeros in the image, and continuing to the next readable sector, ensuring you get as much data as possible. Significant challenge for forensic investigators. You connect and image them using a write blocker, just like a traditional hard drive. However, the internal architecture is fundamentally different. SSDs use a technology called NAND flash memory, managed by a complex controller. To maintain performance, SSDs employ background processes known as trim and garbage collection. When a user deletes a file, the OS sends a trim command telling the SSD which blocks are no longer needed. The SSD's controller then actively erases these blocks in the background to prepare them for new data. This means that unlike on a traditional hard drive, where deleted data sits until overwritten, data on an SSD can vanish completely within minutes of deletion, even without new data being written. Crucially, standard write blockers only stop commands from your computer. They cannot stop the SSD's internal firmware from executing these garbage collection routines once power is applied. Therefore, while you still create a forensic image, you must manage expectations. Recovering deleted files from an SSD is often impossible. Moving on to mobile devices like smartphones, we face a completely different set of hurdles. Unlike standard drives, you can't just pop out the memory card and image it easily. These devices run locked, proprietary operating systems with layers of robust encryption. For mobile phones, we generally have two main acquisition methods. First is logical acquisition. This method communicates with the phone's operating system, essentially asking it to hand over data. It's relatively fast and retrieves what a user would typically see: active contacts, text messages, call logs, and photos. However, it generally will not recover deleted items or data hidden deep within system folders. The second method is physical acquisition. This is the gold standard as it attempts a bit-by-bit copy of the device's physical memory chip. Just like with hard drives, this captures everything, including deleted data stored in unallocated space. However, due to modern encryption and hardware security, performing a physical extraction is extremely difficult, requires expensive specialized hardware and software, takes a long time, and is simply not possible on many modern devices without knowing the passcode. The process isn't over once the progress bar hits 100%. The final crucial steps are verification and documentation. How do we prove to a court that the file on our computer is identical to what was on the suspect's drive? We use cryptographic hashing. Before and after imaging, forensic software calculates a hash value, a unique, fixed-length string of characters like a digital fingerprint, for the source data and the resulting image file. Common algorithms include MD5 and SHA-256. If even a single bit of data is different, the resulting hash values will not match. A matching pair of hashes is mathematical proof that your forensic copy is a perfect, unaltered duplicate of the original evidence. Finally, you must maintain a meticulous chain of custody log. This is a chronological documentation that records every single person who handled the evidence, what they did with it, when they did it, and why. Any gap in this paperwork can lead to the evidence being dismissed in court. In conclusion, creating a forensic copy is the bedrock upon which a successful digital investigation is built. It is the process that allows us to move from a physical crime scene to a digital one without contaminating the evidence. As we've seen, the tools and techniques must be adapted to the specific medium, whether it's a 50-year-old hard drive technology, a modern self-erasing SSD, or a highly secured smartphone. The core principles, however, remain constant. Never alter the original evidence, always use a validated write blocker, and meticulously verify your work with cryptographic hashes and detailed documentation. The field of digital forensics is constantly evolving, so it is your duty as a practitioner to stay informed about new hardware, software updates, and changes in best practices. That's it for this video. If you learned anything, please remember to give us a thumbs up and subscribe. And until next time, be careful what you click.